I'm Daniel Kane. Welcome to the Data Structures and Algorithms specialization. For this very first lecture, we're going to start at the very beginning and talk about why do you need to study algorithms in the first place. So the basic goal in this lecture is to sort of talk about what are the sorts of problems that we're going to be discussing in this algorithms class and why they're important. And in the context of doing this, we're also going to discuss some problems that you might run into when writing computer programs that might not actually require sophisticated techniques that we'll be discussing in this course. And on the other hand, we'll discuss some other sorts of problems that you might want to solve that go beyond the sort of material that we'll be talking about here. So to begin with, suppose that you're writing a computer program. There are a lot of tasks that you might want to perform that you don't really need to think about very hard. These are things like displaying a given text on the screen, or copying a file from one location to another, or searching a file for a given word.
I also wash my teeth so I can sleep when I'm scoring. It's like boring to you, I always say. And I will watch the video. Okay.
Each of these algorithms has essentially a linear scan. You go through every word in the file one at a time, and you do the appropriate thing. And for each of these problems, there's essentially a linear scan that you really can't do much better than. In order to do whatever task it is you're doing, you have to go through all of the data one at a time and process it appropriately. And so when you do more or less the obvious thing, you have a program that works, it solves the problem that you need, and it does so approximately as efficiently as you could expect. So for these sorts of problems, you might not have to think very hard about what algorithm you are using. On the other hand, there are some scan that you really can't do much better than. In order to do other problems, actual algorithms problems, where it's not so clear what it is you need to do. For example, you might be given a map and need to find the shortest path between two locations on this map. Or you might be trying to find the best pairing between students in dorm rooms given some sort of list of preferences. Or you might be trying to measure the similarity of two different documents. Now, for these problems, it's a lot more complicated. It's not immediately clear how to solve these problems, and even when you do come up with solutions, often the simple solutions to these problems are going to be far too slow. You could end up with some simple algorithm. You could try all possible pairings between people in dorm rooms and return the one that optimizes some function that you're trying to deal with. On the other hand, if you did that, it would probably take a very, very, very long time. And you might not have enough time to wait, and so you might need to do something better. And then, even once you have a reasonably efficient algorithm for these problems, there's often a lot of room for further optimization. Improve things so that things run in an hour rather than a day, or a minute rather than an hour, or a second rather than a minute. And all of these improvements will have a large effect on how useful this program you've written is. Now, on the other hand, there are some things that you
just one question. Do you still have headache? Okay.
might want to try and do with your computer that go a little bit beyond the sort of things we're discussing in this course. We might want to call these artificial intelligence problems. And these are problems where it's sort of hard to clearly state what it is that you're trying to do. An example of this might be to try and write a computer program to understand natural language. That is, write a program where I can type something in, some English sentence, asking it, what's the price of milk at the local food store today? And you want the computer to then take this sentence that I wrote and figure out what it means, figure out some way to parse it, and then do an appropriate lookup and return a useful answer to me. And the problem with doing this isn't so much that anything involved here is actually difficult to perform, but the problem is that fundamentally we don't really understand what it means to interpret an English sentence. Now, I mean, we can all speak English, hopefully, if you're listening to this lecture, but we don't sort of really fundamentally understand what it means. It's hard to put it into precise enough language that you can actually write a computer program to do that. Now, you have similar problems, like if you want to identify objects in a photograph. If you've got a picture with maybe a dog and a tree and a cloud, and you want a computer to identify what's what, then once again, this is a thing that our brains have gotten very good at doing, and we understand what the question is. However, it's hard to really put into words how you identify that this thing's a dog and this thing's a tree, and this sort of business makes it very difficult to teach a computer to do the same thing. Another thing that you might want to do is teach a computer to play games well, like play chess effectively. And once again, this is a thing where we can sort of identify what it means to do this, but actually how you want to do it, there's a lot of sort of very vague, intuitive things that go on there. It's not a clearly defined problem that you're trying to solve. And so for all of these problems, sort of the difficulty is not so much that it's hard to do things quickly, but it's hard to even state what it is that you're trying to do and figure out how to approach it. Now, these are problems that we're not going to really cover in this class. We're going to focus on algorithms, how to do things quickly and efficiently. But if you do want to get into AI and want to try and solve these problems, it will be very important that you have a solid grounding in algorithms so that once you have some idea of what does it mean to identify trees in pictures, you will have an idea of what sort of algorithms can actually support these ideas, which sort of ideas you can actually implement in a reasonable amount of time. And so what we're going to focus on these course are the algorithms problems. So we want problems that are cleanly formulated, like clear mathematical problems. And some of the things we looked at maybe aren't immediately clear, like if you want to find the shortest route between 2 points on a map, that's not immediately a math problem. But pretty quickly you can interpret it as such. You can say, well, I want some sequence of intersections I'm traveling between, such that each pair is connected by a road, and the sum of the lengths of the roads is as small as possible. And so pretty quickly this just becomes a problem where we can very clearly state what it is that we're trying to do, but for which it is still non-trivial to solve it. And so that's the sort of thing we're going to be talking about in this class. And hopefully by the end of it, you will have a good idea of how to solve these problems, how to write programs that will solve them very quickly and very efficiently. And that's what we'll be talking about. I hope you enjoy the rest of the class. Hello, everybody. Welcome back to the Data Structures and Algorithms specialization. Here, I just want to give you sort of a brief heads up about what we're going to be talking about in the next 2 lectures. So in the next 2 lectures, we're going to dive right in and we're going to look into a couple of algorithms problems. In particular, we're going to talk about algorithms for computing Fibonacci numbers and algorithms for computing greatest common divisors. Now, these might feel a little bit weird for the very first algorithms that we're going to talk to you in a class. They're kind of number theoretic and numerical, and they won't actually be that similar to what we'll be talking about in the rest of the class. So you might wonder why we're looking at them and what you should be paying attention to. And that's really what I want to talk to you today about. In particular, these 2 topics were chosen because they were the clearest examples we could think of for why algorithms are critically important, why coming up with a good algorithm is really so important on so many problems. And in particular, both of these problems have the following very interesting properties. To begin with, both of these problems have a pretty straightforward algorithm. One where you sort of take the definition of the problem that you're trying to solve, and from that you more or less immediately extract an algorithm. You sort of take the words that you have and you sort of interpret them as an algorithm, and more or less immediately you have some code, and it works, and it computes the things that you want it to compute. Unfortunately, in both cases, these very straightforward algorithms are far, far too slow. You end up with algorithms that take thousands of years to run, even on very modest inputs. And this is not acceptable for practical purposes. You really don't have millennia to wait for your computation to finish, and so you need something better. And it turns out, in both of these cases, there is something better. There's going to be a slightly more complicated algorithm, something that maybe requires one or two bright ideas to get it to work. This slightly more complicated algorithm works fine and is actually incredibly fast. You can handle sort of any reasonable instance of these problems in the blink of an eye. And so the whole point of this is to really show with these very concrete examples that, at least in these instances and in many others that we'll see throughout the course, finding the right algorithm can make all the difference in the world. It's the difference between having an algorithm that takes more time than you will have in your life to finish, and an algorithm that is done before you even knew it started. And so, really, this is what you should be paying attention to, why it is so, so important that we find good algorithms. So that's what's coming up. I hope you enjoy the next couple of lectures. Hello, everybody. Welcome back. Today we're going to start talking about Fibonacci numbers and algorithms to compute them. In particular, in this lecture, we're just going to introduce the sequence of Fibonacci numbers and talk a little bit about their properties. So, to begin with, the Fibonacci numbers is a fairly classically studied sequence of natural numbers. The 0th element of the sequence is 0, the first element is 1, and from there on, each element is the sum of the previous two. So 0 and 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and then the sequence continues, 8, 13, 21, 34, and so on. So it's a nice sequence of numbers defined by some pretty simple recursive rule, and it's interesting for a number of reasons. It has some interesting number theoretic properties, but originally the sequence was developed by an Italian mathematician as a mathematical model. And it's a little bit weird. You might try and wonder what sorts of things this could be a model for. Well, it turns out that originally this was used as sort of a mathematical model for rabbit populations. There was some idea that if you had a pair of rabbits, it would take them one generation to mature, and every generation thereafter they'd produce a pair of offspring. And if you work out what this means, then you find out the Fibonacci numbers tell you how many pairs of rabbits you have after n generations. Now, because rabbits are known for reproducing rather quickly, you might assume that this sequence therefore grows quickly. And in fact, it does. It's not hard to show that the nth Fibonacci number is at least 2 to the n over 2 for all nth Fibonacci numbers. It's not hard to show, therefore grows quickly. And in fact, it does. It's not hard to show that the nth Fibonacci number is at least 2 to the n over 2 for all n at least 6. And the proof can be made by induction. You prove this directly for n 6 or 7 just by computing the numbers and showing that they're big enough. And after that point, f of n is the sum of fn minus 1 and fn minus 2. By the inductive hypothesis, you bound that below and do a little bit of arithmetic, and it's bounded below by 2 to the n over 2. So that completes the proof. In fact, with a little bit more work, you can actually get a formula for the nth Fibonacci number as roughly 1. In fact, with a little so that completes the proof. In fact, with a little bit more work, you can actually get a little bit of arithmetic, and it's bounded below by 2 to the n over 2. So that completes the proof. In fact, with a little bit more work, you can actually get a formula for the nth Fibonacci number as roughly 1 square root of 5 over 2 to the n. These things grow exponentially quickly. And well, it turns out it means then you find after n generations. Using rather quickly this sequence. And the proof can be made by induction. You prove this directly for n 6 or 7 just by computing the numbers and showing that they're big enough. And after that point, f of n is the sum of fn minus 1 and fn minus 2. By the inductive hypothesis, you bound that below and do a little bit of arithmetic, and it's bounded below by 2 to the n over 2. So that completes the proof. In fact, with a little bit more work, you can actually get a formula for the nth Fibonacci number as roughly 1 square root of 5 over 2 to the n. These things grow exponentially quickly. And these things roughly Fibonacci number. In fact, with a little bit more work, you can actually get a formula for the nth Fibonacci number as roughly 1 square root of 5 over 2 to the n. These things grow exponentially quickly. And to sort of drive that home a little bit more, we can look at some examples. The 20th Fibonacci number is 6,765. The 50th Fibonacci number is approximately 12 billion. The 100th Fibonacci number is much, much bigger than that. And the 500th Fibonacci number is this monster with something like 100 digits to it. So these numbers do get rather large quite quickly. So the problem that we're going to be looking into for the next couple of lectures is how do you compute Fibonacci numbers. So if you want to use them to model rabbit populations or because of some number theoretic interest, we'd like an algorithm that as input takes a non-negative integer n and returns the nth Fibonacci number. And we're going to talk about how you go about doing this. So for work, you can actually get a formula for the nth Fibonacci number as roughly 1 square root of 5 over 2 to the n. These things grow exponentially quickly. And to sort of drive that home a little bit more, we can look at some examples. The 20th Fibonacci number is 6,765. The 50th Fibonacci number is approximately 12 billion. The 100th Fibonacci number is much, much bigger than that. And the 500th Fibonacci number is this monster with something like 100 digits to it. So these numbers do get rather large quite quickly. So the problem that we're going to be looking into for the next couple of lectures is how do you compute Fibonacci numbers. So if you want to use them to model rabbit populations or because of some number theoretic interest, we'd like an algorithm that as input takes a non-negative. Hello everybody, welcome back. Today we'll talk a little bit more about how to compute Fibonacci numbers. And in particular today what we're going to do is we're going to show you how to produce a very simple algorithm that computes these things correctly. On the other hand, we're going to show that this algorithm is actually very slow and talk a little bit about how to analyze that. So let's take a look at the definition again. The 0th Fibonacci number is 0, the first Fibonacci number is 1, and from thereafter each Fibonacci number is the sum of the previous two. Now these grow pretty rapidly, and what we would like to do is have an algorithm to compute them. So let's take a look at how we might do this. Well, there's a pretty easy way to go about it given the definition. So if n is 0, we're supposed to return 0, and if n is 1, we're supposed to return 1. So we can just start with a case that says if n is at most 1, we're going to return n. Otherwise, if n is at most 1, we're going to return n. Otherwise, what are we supposed to do? Otherwise, we're supposed to return the sum of the n minus first and n minus second Fibonacci numbers. So we can just compute those two recursively, add them together, and return that. So this gives us a very simple algorithm, 4 lines long, that basically took the definition of our problem and turned it into an algorithm that correctly computes the thing it's supposed to. Good for us. We have an algorithm and it works. However, in this course, we care a lot more than just does our algorithm work. We also want to know if it's efficient. So we'd like to know how long this algorithm takes to run. And as sort of a rough approximation to this, we're going to let t of n denote the number of lines of code that are executed by this algorithm on input n. So to count this is actually not very hard. So if n is at most 1, the algorithm checks the if case, goes to the return statement, and that's 2 lines of code. Not so bad. If n is at least 2, we go to the if case, we go to the else condition, and then run a return statement. So that's 3 lines of code. However, in this case, we also need to recursively compute the n minus first and n minus second Fibonacci numbers. So we need to add to that however many lines of code those recursive calls take. So all in all, though, we have a nice recursive formula for t of n. It's 2 as long as n is at most 1. And otherwise, it's equal to t of n minus 1 plus t of n minus 2 plus 3. So a nice recursive formula. Now, if you look at this formula for a little bit, you'll notice that it looks very similar to the original formula we used to define the Fibonacci numbers. Each guy was more or less the sum of the previous two. And in fact, from this you can show pretty easily that t of n is at least the nth Fibonacci number for all n. And this should be ringing some warning bells, because we know that the Fibonacci numbers get very, very, very large. So t of n must as well. In fact, t of 100 is already 1.77 times 10 to the 21, 1.77 sextillion. This is a huge number. Now, suppose we were running this program on a computer that executed a billion lines of code a second. In fact, t of 100 then must as well. In fact, t of 100 is already 1.77 times 10 to the 21, 1.77 sextillion. This is a huge number. Now, suppose we were running this program on a computer that executed a billion lines of code a second. It ran at a gigahertz. It would still take us about 56,000 years to complete this computation. Now, I don't have 56,000 years to wait for my computer to finish. You probably don't either. So this really is somehow not acceptable if we want to compute Fibonacci numbers of any reasonable size. So what we'd really like is we'd like a better algorithm, and we'll get to that next lecture. But first, we should talk a little bit about why this algorithm is so slow. And to see that, maybe the clearest way to demonstrate it is to look at all of the recursive calls that this algorithm needs in order to compute its answer. So if we want to compute the nth Fibonacci number, we need to make recursive calls to compute the n minus first and n minus second Fibonacci numbers. To compute the n minus first, we need the n minus second and n minus third. To compute the n minus second, we need the n minus third and n minus fourth. And it just keeps going on and on from there, and we get this big tree of recursive calls. Now, if you'll look at this tree a little bit closer, it looks like we're doing something a little bit silly. We're computing fn minus 3 3 separate times in this tree. And the way that our algorithm works, every time we're asked to compute it, since it's a new recursive call, we compute the whole thing from scratch. We recompute fn minus 4 and fn minus 5 and then add them together and get our answer. And it's sort of this sort of computing the same thing over and over again that's really slowing us down. And to make it even more extreme, let's blow up the tree a little bit more. Fn minus 4 actually gets computed these 5 separate times by the algorithm. And as you keep going down, more and more and more times are you just computing the same thing over and over again. And this is really the problem with this particular algorithm, but it's not clear immediately that we can do better. So come back next lecture and we'll talk about how to get around this difficulty and actually get a fairly efficient algorithm. Immediately that we can do better. So come back next. Hello everybody, welcome back. We're still talking about algorithms to compute Fibonacci numbers. And in this lecture, we're going to see how to actually compute them reasonably efficiently. So as you'll recall, the Fibonacci numbers was the sequence, 0, then 1, then a bunch of elements, each of which was the sum of the previous two. We had a very nice algorithm for them last time, which unfortunately was very, very slow, even to compute the 100th Fibonacci number, say. So we'd like to do better, and maybe you need some idea for this new algorithm. And one way to think about it is, what do you do when you compute them by hand? And in particular, suppose we want to write down a list of all the Fibonacci numbers. Well, there's sort of an obvious way to do this. You start off by writing 0 and 1, because those are the first two. The next one is going to be 0 plus 1, which is 1. The next one is 1 plus 1, which is 2, and 1 plus 2, which is 3, and 2 plus 3, which is 5. And at each step, all I need to do is look at the last two elements of the list and add them together. So 3 and 5 are the last two, I add them together, and I get 8. And this way, since I have all of the previous numbers written down, I don't need to do these recursive calls that I was making in the last lecture that were really slowing us down. So let's see how this algorithm works. So what I need to do is I need to create an array in order to store all the numbers in this list that I'm writing down. The 0th element of the array gets set to 0. The first element gets set to 1. That's to set our initial conditions. Then as I runs from 2 to n, we need to set the ith element to be the sum of the I minus first and I minus second elements. That correctly computes the ith Fibonacci number. Then at the end of the day, once I've filled out the entire list, I'm going to return the last element, f of n. So now we can say this is another algorithm. It should work just as well, but how fast is it? Well, how many lines of code do we use? There are 3 lines of code at the beginning, and there's a return statement at the end, so that's 4 lines of code. Next up, we have this for statement that we run through n minus 1 times, and each time we have to execute 2 lines of code. So adding everything together, we find out that t of n is something like 2n plus 2. So if we wanted to run this program on input n equals 100, it would take us about 202 lines of code to run. And 202 is actually a pretty small number, even on a very modest computer these days. So essentially, this thing is going to be trivial to compute the 100th or the 1000th or the 10,000th Fibonacci number on any reasonable computer. And this is much better than the results that we were seeing in the last lecture. So in summary, what we've done in this last few lectures, we've talked about the Fibonacci numbers, we've introduced them. We've come up with this naive algorithm, this very simple algorithm that goes directly from the definition, that unfortunately takes thousands of years, even on very small examples, to finish. On the other hand, the algorithm we just saw is much better. It's incredibly fast, even on fairly large inputs, and it works quite well in practice. And so the moral of the story, the thing to really keep in mind, is that in this case and in many, many others, the right algorithm makes all the difference in the world. It's the difference between an algorithm that will never finish in your entire lifetime and one that finishes in the blink of an eye. And so that's the story with Fibonacci numbers. Next lecture, we're going to talk about a very similar story that comes with computing greatest common divisors. So I hope you come back for that. Until then, farewell.
Welcome to the Linux Foundation specialization. In this specialization, there are 4 courses that cover the foundations of Linux administration. All right, so upon completion of the specialization, I want you to be able to do several things. You should be able to view, create, copy, move, and remove files from your Linux system. You should be able to search and analyze text on a Linux system. You should be able to configure network connections, users, and groups. You should be able to manage disks and software packages. You should be able to secure that Linux system. We'll talk about both securing it internally, the permissions, authentication, and authorization, but also perimeter security. And you should be able to compare and contrast cloud computing models, virtualization, and containers. These are buzzwords we hear a lot of today that use Linux, but I want you to really be able to understand them and think about which is the right solution for the problem you're trying to solve. All right? All right, in this specialization, the first course is Linux Fundamentals. The second course is Managing Linux Systems. We'll then follow up with Securing Linux Systems, and then we'll conclude with Linux Cloud and DevOps in the 4th course. All right? All right, there are 2 other courses that are not part of the specialization, but are bundled together in what we call the Professional Certificate for LFCA, Linux Foundation Certified IT Associate. That's a professional certification out there. And you can take an exam that will test your knowledge of fundamental IT concepts, including operating systems, software application installation and management, hardware installation, use of the command line and basic programming, basic networking functions, security best practices, and other related topics to validate your capability and preparedness for an entry-level IT position. So I have a link here so you can get to more information about certification. But there's 2 courses combined with the specialization. One is a practice where we'll have more lab opportunities to practice the kind of things you should know for the certification. And lastly is an exam prep where we'll have some sample tests and we'll talk about the exam in that course. All right, I hope you enjoy the specialization and learn a lot. See you in the courses. For the certification. And Welcome to Linux Fundamentals. Linux Fundamentals is the first course in the Linux Foundation specialization. The first module here, we're going to think about the Linux operating system. All right, so by the time we're done with this first module, there's many things I want you to be able to do. And what I mean by things I want you to be able to do, you should be able to do them, but you should also be able to be assessed on them in the quizzes and tests, okay? So you should be able to list several Linux distributions. You should be able to describe Linux services. You should be able to view, create, copy, move, and remove files on the Linux file system. And lastly, you should be able to search and analyze text. All right, so in this first lesson, we're going to think about the history of Linux. So first off, what is Linux? So when we say Linux, we mean one of many specific distributions in a family of open source Unix-like operating systems. Okay, they're all based on the Linux kernel that was developed by Linus Torvalds. And these are typically bundled in what we call a Linux distribution. We'll talk about all these terms through this module. So don't stress if a lot of what I just said didn't make sense. We're going to get there, okay? Linux was originally developed for the personal computer, which is the x86 architecture. That's the same architecture that we use for Windows machines, for Macintosh machines today. So very popular architecture used in home. It was then ported to many other platforms. These are typically servers that are out in the internet and the cloud today. So very successful. It's also used in Android. So Android, which is Google's smartphone, which has at least half of the smartphone market, uses Linux. Chromebooks, which have become very popular, again from Google, they have a Chrome OS that uses Linux. And many embedded systems also run Linux. And about 90% of all the cloud infrastructure is powered by Linux. So Linux is out there and very popular and very important to our society. So let's take a step back and think about those embedded systems. So there are many different embedded systems. The difference is a generic system is what we call a personal computer. You can use it for many things. You can use it for creating music, for watching videos, for learning, for doing Excel and accounting, those sorts of things, for programming, right? It's generic. Embedded systems have one purpose. So some examples are a home router or a router in your company that's going to route traffic between your private network and your public network. Automation control systems in industry, smart home technology, things like our thermostats today or our sprinkler systems. All of our televisions now come with an embedded system, so we can install channels like Peacock or Netflix or Amazon Prime, and new channels can come along that are developed or updated after our television has been released. Our automobiles have many embedded systems. Our digital video recorders, our video game consoles, our smartwatches, right? They're everywhere nowadays, and it's going to keep growing. And a lot of these run Linux. So how is Linux different? Linux has many advantages over other operating systems. This includes it's open source. Now we're going to drill into what we mean by open source, but the one-liner is you're able to see the source code, make changes, and share it with other people. That's not true of other operating systems. We'll come back to this. It's community supported. Because it's open source, there's lots of people who can provide support. You're not locked into one vendor for support. It supports older hardware, right? In the other world, the operating systems try to get you to upgrade your hardware all the time, right? That becomes expensive. Linux will actually work on older machines. All right, to think about the precursors to Linux, Unix was developed in 1969 by Bell Labs. Bell Labs was owned by AT&T, which was a monopoly that owned the phone service. And AT&T, because it was a monopoly, was required to license the Unix operating system source code to anyone who asked. And then in 1984, when the government split up AT&T, it divested itself of Bell Labs, and Bell Labs began selling Unix as a proprietary product. At that time, the GNU project started up. And the goal of GNU was creating a complete Unix-compatible software system composed of entirely free software. This doesn't necessarily mean free in dollars, but free in use. And again, we'll keep talking about this concept later on. So in 1985, Richard Stallman started the Free Software Foundation. In 1989, Stallman wrote the GNU General Public License. We call that GPL or GNU GPL. And then by the early 1990s, many of the programs required in an operating system were completed. So these include things like the libraries we link our source code to, the compilers that convert our human readable text to machine readable code, the text editors, the command line shell, and a windowing system similar to Mac and Windows. Okay, another early project was Minix. It was created by Andrew Tannenbaum. Andrew Tannenbaum is a famous operating system computer scientist. And this was a minimal Unix-like operating system targeted at students and others who wanted to learn operating system principles. And Tannenbaum shared the complete source code of Minix, but the licensing terms prevented it from being free software, meaning you couldn't change Minix and share it with other people. Today, Minix 3, which is the latest version, is a free open source operating system similar to Linux. But really, the ship had sailed, right? Linux became popular, and so it's really kind of too late for Minix, but it's still there to learn from. All right, so let's think a little bit about Linus Torvald. In 1991, he was attending the University of Helsinki, and he became curious about operating systems. And he tried to build his own operating system kernel, which eventually became what we call the Linux kernel today. And it was originally developed for Minix and used Minix tools. But then he switched the license to use the GNU GPL and the tools from GNU project. All right, that's it for lesson 1. So GNU project. GPL and the tools from GNU project. And the tools from GNU project. All right, that's it for lesson 1. So just a little review here. Unix was owned and licensed by Bell Labs. The Free Software Foundation created GNU tools as part of the GNU project. And Linus Torvalds created the Linux kernel and used the GNU tools ultimately, and that's how we ended up with Linux today. All right, I'll see you in the next lesson. Welcome back to the Linux operating system. In this lesson, we're going to drill into the Linux licensing model. So we talked about the GNU GPL. GPL stands for General Public License. The Linux kernel and the code from the GNU project are all licensed under GNU GPL, which means you can freely copy the source code, you can change it, and then you can distribute those changes. What you cannot do is impose any restrictions on further distribution. So if you're giving someone your changes, you can't control what they do with it. Besides, it has to be licensed under the GPL. So when you make changes and you share them with the community, if anyone then improves your changes, they have to share those with the community. But that's what we meant by community support in that last lesson. So you're probably saying, how do companies make money on Linux? Well, some distributions charge for a supported release. Consultants charge for the installation and customization of Linux, because once you become an expert, people want to hire experts. And cloud companies do not distribute because they're not giving their code, so there's no need to share the source code. Many commercial companies gave up their own OS work and embraced Linux to compete with Microsoft Windows. This includes IBM, Hewlett-Packard, Dell. Right? The idea is, let's take Linux, embrace it, and add features to it so we can now charge for distributions potentially and services and compete with Microsoft Windows. All right, a little review here. Open source does not mean you cannot charge for Linux. It means you have to allow someone to have the source code if you give them Linux, and you have to allow them to share those changes also. If you give someone your changed Linux executable, you have to give the source code with it. And everyone has the right to change and add to Linux. All right, see you next time.